In this video, we're going to look at water's equilibrium and the equilibrium expression that we use for that, how we can measure pH, and what may be to you a relatively new measurement, pOH. We're going to define strong acids and strong bases and look at neutralization reactions. Electrolytes are important compounds when we're talking about aqueous solutions. An electrolyte is a compound that's going to dissociate into ions when it's dissolved in water. Most of these compounds we then consider to be ionic. We can classify electrolytes based on how well they will dissociate or split apart into ions when they're placed in the water. A strong electrolyte is going to be a compound that's going to dissociate approximately 100%. A weak electrolyte is going to be a compound when placed in the water that's going to dissociate only about 1 to 10%. Non-electrolyte is going to be a compound that will dissolve in water, but it doesn't dissociate into ions when you dissolve it in water. These definitions for strong and weak electrolyte are important because they lead us to our definition of what we consider to be strong and weak acids and bases. A strong base is going to be a compound or an acid that is going to react with water close to 100%. A weak acid is going to be a compound that's going to react with water approximately to 1 to 10% extent. A strong base is going to dissociate in water close to 100%. And a weak base is going to react with water to a much smaller extent, about 1 to 10%. So you see our definitions for strong and weak acids and bases follow this definition for strong and weak electrolytes. Because we can classify acids and bases as being strong or weak, we need to have a way of recognizing them. The easiest way to recognize an acid or a base as strong or weak is simply to memorize the strong acids and bases. There are only a few strong acids and bases compared to the many thousands of what can be considered weak acids and bases. So we'll see that the strong acids, there are 6 of them: hydrochloric acid, hydrobromic acid, and hydroiodic acid. Those are our strong binary acids. For our oxoacids, or also called oxyacids, we have nitric, sulfuric, and perchloric acid. The strong bases basically are just any compound that has the hydroxide from group 1A and group 2A. One thing to note is that the hydroxides in group 2A, when we studied solutions, we saw that these are not very soluble compounds. The thing is that our definition for a strong base isn't based on how well it dissolves. What the definition of a strong base is defined by is how much it dissociates. And although not very soluble, these compounds will dissociate close to 100% when they're dissolved in water. We've introduced the water self-ionization reaction when we first introduced acids and bases. What we're going to look at now is how do we use this equation in our equilibriums. Now, as we've seen with some equilibrium expressions, we write it out so that we do not include any liquids and solids. For that reason, the water molecules that we have on the left-hand side or the reactant side are not included in our equilibrium expression. This equilibrium expression is special, so we give it a special symbol, Kw. And the value for Kw measured at 25 degrees Celsius is 1 times 10 to the negative 14th. Since most of our reactions are done in the lab at 25 degrees Celsius, this is the constant we're going to use. But keep in mind, changes in temperature can cause a change in this equilibrium value. Now for water is neutral because with just pure water, the production of the hydronium and hydroxide ion is equal. If we were to add a compound that would change one of these concentrations, we would see a corresponding increase or decrease. If a compound added hydronium ions, we would have an increase in hydronium's concentration with a corresponding decrease in hydroxide. Again, so that we can keep that value of K the same. For all of our aqueous solutions, this equilibrium equation is going to be in the background. And it also then leads to how we measure what we call pH and pOH. P in the pH and pOH, and any other measurement that you would see that has P at the beginning, represents the negative log. So what we're going to be doing is taking the negative log of some value. pH is a measure of the hydronium ion concentration. As we've seen already, hydronium determines whether something's going to be an acid or a base. If we have a high concentration of hydronium, we are going to have a low pH. Numerical values, when assigned, a solution that has a pH below 7 is considered to be acidic. A pH of 7 is considered to be neutral, and a pH of above 7 is going to be considered basic. The formula for pH is the negative log of the hydronium ion concentration. If you're given the hydronium ion concentration on your calculator, you simply would punch negative log and then plug in the concentration for the hydronium. When you hit enter, you would have the pH. pOH is a measure of the hydroxide ion concentration. In this case, if we have a low pOH, we have a high concentration for hydroxide. So a solution that has a pOH below 7 is going to be basic. If it has a pOH of 7, it will be neutral. And if it has a pOH of above 7, it's going to be considered acidic. Notice that these two scales are the exact same thing. It's just we're measuring different ions. pH is measuring the hydronium, pOH measuring the hydroxide. The equation is also essentially the same. We're just measuring the hydroxide ion concentration. And the way it's calculated would still be the same. You take the negative log and you plug in the concentration for the hydroxide. The equation for the equilibrium of water is given here below. If we were to take the negative log of this equation, we would get the negative log of Kw, the negative log of H3O, plus the negative log of hydroxide. And the reason why we're doing the addition is because when you take the logarithm of two things that are being multiplied, that multiplication turns into addition. Because negative log can be represented by the letter P, that would give us pKw equals pH plus the pOH. And so this shows us the relationship that is defined by the equilibrium constant in a simpler mathematical equation. pKw is the negative log of 1 times 10 to the negative 14th. That would equal 14. All pHs and pOHs then will equal a sum of 14. We can then use pH and pOH with this relationship to easily find one or the other. If given pH, you can easily find pOH. If given pOH, you can easily find pH. Now, when we're talking about the pH of strong acids and strong bases, the calculations are relatively straightforward. Strong acids react completely in aqueous solution, so all of the hydrogens that are in an acid will react to form the hydronium ion. Therefore, the concentration of the hydronium ion will equal the concentration of the acid. Strong bases the same way. Since strong bases dissociate completely in aqueous solution, the hydroxide ion concentration from the base is going to equal the base concentration as long as it has only one hydroxide. If the formula has two hydroxides, the concentration of the hydroxide is going to be twice the concentration of the base. And we see below a couple of examples. If I have a 0.1 molar concentration of hydrochloric acid, I'm going to get 0.1 molar hydronium. If I have 0.05 molar nitric acid, I'm going to have 0.05 molar hydronium. With the sodium hydroxide, 1.50 molar sodium hydroxide would give me 1.50 molar hydroxide ions. But if I have a 0.01 molar calcium hydroxide, because there are two hydroxides in that compound, it will dissociate into 2 moles of that hydroxide ion, doubling our concentration. Reactions between acids and bases are called neutralization reactions. I think everybody has a pretty decent understanding coming into the chemistry class that a neutralization occurs between acids and bases. When we look at reactions between strong acids and bases, really all we're looking at is a double replacement reaction. The products of this acid-base neutralization will be water and another compound that we call salt. Salts are basically ionic compounds. Now, we've talked about equilibrium reactions. And strong acids and bases, when they react, really don't form an equilibrium. The reaction goes one direction, and there isn't much to be considered in the reverse direction. And when we're doing stoichiometry problems with neutralization reactions, they're just solution stoichiometry problems. There's nothing special. We're going to have volume, we're going to have molarity. Those calculations are relatively straightforward. The reactions will look like this. We'll have an acid, represented here by the symbols HA. We'll have a base, strong base, represented by the symbol XO, where the X is going to be some metal, producing water, and a salt, represented by XA, the metal cation with an anion. Hydrochloric acid and sodium hydroxide is going to produce water and sodium chloride. Another example would be nitric acid and calcium hydroxide. In this case, calcium hydroxide's got two hydroxides to react. That's giving us our two waters and calcium nitrate.